click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to the subject of machine design 1. In last lecture we have seen some design aspects of power screw and some important formulae. The list of formulae is really lengthy, but let us solve it because it will give you in-depth idea of how the design of power screw is done. Because on the basis of power screw design only, the screw jack design is based or majority part will be taken. Once you learn this power screw design, it will be helpful for design screw jack and power screws. Fine. So let us move ahead. Let us start with the numerical. So numerical on design of power screw part 1. The problem statement is given. In a random power statement, the problem statement will be given where material will be either specified or we'll have to select the material. So it says that for a load of 100 kilonewton, so the load given is 100 kilonewton, to be lifted to 500 mm. This is the height to which the load is to be lifted. Design a power screw only. So they have kept our purpose limited only to the power screw design. So let us begin with it. We know that very first step is write down the given data. So we have been given load P is equal to 100 kilonewton. Now again we know that we need to consider design load. So higher margin we need to consider. So let us consider again 30%. Let 30% be the higher margin of load, and therefore the design load P becomes 1.3 times 100. So that is somewhere 130 kilonewton. So we'll be solving our problem for 130 kilonewton. The second step is important, and there we'll go for the material selection. Now again, if the material is specified by the problem statement itself, it's fine. Otherwise, we'll have to select. So again, from PSG 1.10, you can go for different applications which are required for this particular material selection. So there are many materials which can be used for this particular kind of machine parts. Let us go for C40 as the material because that is generally used for the spindles. Spindles are kind of things which are related with power screw. So we'll go for C40 or C60. It's up to you. Accordingly, material properties will change. Of course, cost is not a concern for us right now, so you can select that material, but it should be in line with the application. So let C40 be the material. So from PSG 1.9 will get its values, the material values. So sigma y, because it's a ductile material, the sigma y we will get from 1.9 is 330 Newton per millimeter square. So that is what the value we are going to consider. Now again we have to consider some factor of safety. Now power screws actually have very heavy applications to consider. So we'll go for a better power of safety. In this case we are going to look at power of safety somewhere around 5 to 10. So let us begin with the initial part. If it fails, we have to come back and change factor of safety. So let FOS be equal to 5, and therefore your sigma allowable or sigma tension is equal to 330 divided by 5. So the value comes out to be 66 Newton per millimeter square is the allowable stress value that we have. So this is another thing for ductile materials. Of course, mainly the value of tensile and compression are same, but we can consider some higher range also. For keeping the design safe, we'll consider it lower value. So let sigma compressive is equal to sigma tensile, and hence it becomes 66 Newton per millimeter square, and the values are allowable. Values. Also, since these are ductile materials, we know that shear strength is exactly half its tensile or compressive, so it becomes 33 Newton per millimeter square. And let us consider the crushing value is equal to 30% higher than the tensile value. So it comes out to be 85.8 Newton per millimeter square. So there we have defined the important material properties, first, second and third, which we are going to consider for the calculation of a safe design. Let us move ahead. The next thing is the design of screw. So let us begin with the design of screw. In this lecture, we are going to look at only about the design of screw. In the next lecture, we'll be dealing with the design of nut and other parameters. So we know that the screw fails mainly under the tensile failure, and hence we know that the tensile load F, you can use letter F, you can use letter P. So F will be given by the area of cross section of the screw. Now we are considering the core diameter into sigma T. The load is been given, we have modified it to 130 kilonewton into 10 raised to 3, which is equal to pi by 4 into core diameter square into the allowable value, which we have figured out is 66. And therefore diameter, the core value that we get, core diameter value we get is somewhere around 50.01 millimeter. Let us consider a higher series. Let us make it 52 millimeter. And hence there we find the first parameter of a power screw, that is the core diameter of the power screw. Now there are standard power screw come. If you remember this, in the first topic itself we had went for learning the standard specimens or the preferred series or standard components like bearings, screws, nuts. They come in standard values. So let us choose the standard values which is in line with our calculation. So for that, you all need to refer to the PSG 5.71. From PSG 5.71, we have the normal series, square threads normal series. Now again, that depends upon the applications. Since no application is mentioned, we have the liberty to go for the standard value. So we have different series with us, some fine series, coarse series, and then we have normal series. So let us go for the normal series, which is the mean of all the series which are available. So considering this normal series, let us match this core diameter value with the minor dia value with this. We know that core diameter value is equal to the normal diameter. So compare with minor diameter, compare with minor diameter. Now comparing with minor diameters available in this particular range with this 52 value, the value that we will prefer is 55. Of course we have the liberty to use 53 also, but let us go for 55, which is the higher range. So selecting standard square threads, we get, now there are certain parameters which we can actually take down. So let us go for nominal diameter nominal, which is equal to 65 millimeter. Then second parameter is major diameter. So D major is 65 again millimeter. Then we'll go for diameter, minor diameter, which already have said. So core diameter is 55 millimeter. Along with which there are some standard values like pitch is 10 millimeter. And the next value that they have given is of no use to us. So these are the major parameters that we need to select from the given series and which are selected by us, right? So with this dimension, let us move ahead for finding out the remaining parameters. So remember, this is our base value as of now, which is available with the standard threads. So let us move ahead. So next thing we are going to find out is the torsion or the torque that is going to act on the body. So this is the core, or this is the basic value which we are going to consider, based on which we are going to do rest of the calculation. Now since we have the major value and the minor value, core diameter is nothing but minor diameter minor. So the mean diameter will be given by their average. So mean diameter comes out to be 60 mm. So we are taking the average of major and minor. So based on this, now further calculation is dependent. Like we said, this particular part, which is the power screw, may fail in tension, may fail in compression, and also it may fail in shear. So to consider the shear aspect, you must find out the torque that it is going to fail under. So for that we already have an empirical relation. You please rememorize this relation, where it's the ratio of f and mean diameter with some factor. The factor has some standard parameters like length, mu, and the rest of the parameters that we already have. Now we also know that for square threads, length is also considered as pitch, so which is 10 millimeter. We already have found out. The second relation is mu, that we may have to consider. For the proper application, for the smooth functioning, mu should not be very large or it should not be very small, because if it is small, power screw will not sustain the given load. It will slide down easily, and if it is very hard, it is going to be very difficult to provide the power. So we'll take some mean value, and let us take mu is somewhere equal to 0.28 for the given considered material, which is carbon steel. So these are the two values which we have considered. Let us find out the torque that this particular screw can sustain. So it is the value F, which is the actual force which we have considered, is 130 kilonewton divided by 2 into the mean diameter, which is 60 mm. The torque which we are going to get will be in terms of Newton millimeter, into length, which is 10 plus 0.28 times pi into dm, again 60, divided by pi into 60 minus 0.28 into 10. When we solve this expression, we will get value of T equals Newton millimeter. We can express this value in terms of meter also. Let us keep this value to be so that will be the value. We'll consider some higher value and we'll go with it. Now comes the stage where we have to consider the combined stresses, and we'll check whether, see, we already have found out the dimensions. We have selected the standard square thread, and for that all the dimensions which we have obtained, let us check whether they are safe in the given conditions or not. So we'll say safety checking. Under this, we know that the best or the failure, they have proved that the best failure theory which is applicable to power screws is the combined stress theory, and for that we have to go for the combined loading. The combined loading which we have considered here are the compressive as well as the shear, and for that we'll consider them. So let us move ahead with checking for combined loading. Combined loading should be considered, and therefore by maximum principal stress theory, we know that principal stresses induce when there is combined loading, and that's why in line with combined loading criteria we are going to consider maximum principal stresses. Maximum principal stresses, stress 1, 2 will be given by the relation between the shear sigma c divided by 2 plus or minus, plus stands for the 1, minus stands for the 2, square root of sigma c by 2 square plus tau square. So in short, we need to find out sigma c and tau. We know that sigma c is given by the load F divided by pi by 4 core diameter square. Now if number of threads are specified, we are going to use the factor n also, otherwise this is the only formula which is required. So its value DC which we have considered right now is 55. Can say the value which we have considered is 55. So using that value we are going to solve this, and therefore sigma c value comes out to be 54.71 Newton per millimeter square. No doubt that since this particular value is smaller than the value that we can use, it is definitely safe in our case. The next thing is we have to find out shear stress. Now the formula for shear stress we have is the torsion is basically given by pi by 16 into d core cube into shear strength. Now this is when your cross section itself is circular. We know that the cross section diameter is dc. So it comes out to be, we already have the value of t, we need to find out value of tau, and hence tau will be given by 16 times torsion divided by pi dc cube. Here substitute the values, 16 into the torsion value which we have found out is this. So it is 1.32 into 10 raised to 6 divided by pi into dc cube, 55 cube. Make sure that all the units stand in the same format. So the value of tau comes out to be 40.40 Newton per millimeter square. This is the induced shear stress. Now, using combined shear stress theory, we can go for the principal stresses. In this case, we are going to compare the principal stresses with the allowable value of stresses. And therefore, principal stresses sigma 1, 2, as we have seen in the formula, are given by, if you remember the formula, it is given in terms of the compressive stress, in terms of shear stress. So it comes out to be, stress which we have found out is 54.71 divided by 2 plus minus square root of 54.71 divided by 2 bracket square plus tau square. Tau we have is 40.40 bracket square, and therefore sigma 1, 2. So it comes out to be 27 plus minus. If we substitute this value, we'll get the answer somewhere equal to 48.59. And therefore, principal stress 1 . So after solving these equations, we are going to get these values as the principal stresses. Now we have to compare these principal stresses with the values that we have. So when we are going to compare these values, this is basically the shear value and this is the compressive value, and that can be found out using their signs, because these two principal stresses are because of the combined stresses, which are the compressive and the shear, and the value which is negative of course is compressive, the value which is positive is shear. So let us compare these values which are the induced stresses with their strengths, right? So we know that the compressive strength, which was equal to tensile strength, we had assumed that was 66 Newton per millimeter square, and the shear stress, the possible value was 33 Newton per millimeter square. So let us compare this, and therefore factor of safety which we will get in our case, since we already have considered factor of safety for this, so these are the allowable values. So considering factor of safety for this also, we'll get sigma principal stress allowable is equal to sigma 1 divided by FOS. In our case, FOS comes out to be, and sigma 2 allowable will be again equal to sigma 2 divided by FOS, which is 5. Sigma 1, which is this, divided by 5 gives us the answer 75.59 divided by 5 gives us 15.118 Newton per mm square, and the sigma 2 value, that is 21.59 divided by 5 gives us 4.318 Newton per millimeter square. So what is the purpose of doing this? See, these are the allowable values which are actually inside the material, which will exist, and these are the maximum allowable value that we can allow to exist. So let us see what is the relation between them. If that relation comes out to be greater than 5, our design is safe, but they come out to be smaller than 5, our design is not that safe. So let us move ahead. Therefore, FOS given by, or we'll say actual FOS in compression, actual FOS compression is given by, as we know, allowable value divided by the working value. The allowable value we had got was 66 in compression, and the working value in compression which we have obtained is 4.318. Let us ignore its sign because that's the compression, we just need the magnitude. So the value comes out to be somewhere equal to 15.28. So that's the factor of safety I get for the compression. Similarly for shear, I get FOS again equal to allowable divided by working, but it's the allowable shear stress which was 33 in our case, and the working stress which we have obtained is 15.118. So FOS in shear we gave is 2.18. Now in our case the factor of safety are already greater than 1, and hence the design is superficially safe. If in some case if factor of safety is mentioned, specified, in that case we have to tally these values with the given factor of safety. Somehow the original factor of safety which we had considered for the design purpose was 5. This is truly safe in that case, but this is truly not safe as that of FOS 5. But somehow since it is greater than 1, we can say that superficially our design is safe, and hence screw is safe in design. So that was from my side about the screw design. In next lecture we'll be looking at the nut design and some other remaining parameters. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.